Good morning. Um, so we are back looking at waves. So last lecture um, we were introducing waves as a disturbance that would propagate through some kind of a medium. And we had looked at velocities of propagation and energy transport formulas. And now we were ready to write down formulas describing the motion of individual pieces of the medium. And so the idea here was to take the medium. So, this was the y-axis. This was, that could be changed to d, huh? I could have done that. And so here is what the medium looks like. And then the formula here was keeping track of how that different parts of the medium are being displaced from the equilibrium location, and we had reached this point. So now this miraculously is now radians per meter. Look at that. So the frequency is in radians per second. The wave number is in terms of radians per meter. So stop and stare at those values. Think about what that's telling us. Let's take a look at a traveling wave. So it says, ooh, there's a lot of stuff on this one too. So it says that we have a horizontal stretched cord and somebody's oscillating. Oh my gosh. So this person is oscillating it, they're oscillating it at 250 cycles per second. And I don't think that happens. I don't think you could manually create that frequency of 250 hertz. That seems like a lot. Anyway, 250 hertz, that's 250 cycles per second. So those are, individual pieces of the medium are oscillating back 250 times a second. The amplitude is 2.6 centimeters. Those are some remarkable numbers. So 2.6 centimeters, that's 2.6 centimeters here and 2.6 here. That's like 5 centimeters back, 5 centimeters back and forth. 250 times a second. I bet the velocities and acceleration numbers are going to be huge for that. All right, so the cord's under a tension of 140 newtons, and it has a linear density of 0.120 kilograms per meter, and at t equals 0, at the time we want to be able to call t equals 0, the end of the cord, now I guess this is what they're calling the end, is this location where it's being driven. So you can think of it as being driven, and again they have y here, it should really be capital D. So the string, the cord here, is going to be oscillating back and forth 250 times per second along the d-axis that we have shown here. All right, so very quickly then, let's take a look. The displacement formula we had shown for a sine or a cosine function. So if we're going to think of these waves as being harmonic, meaning represented as sines or cosines. So for a harmonic wave, let's start with, we went with a sine, kx minus omega t. Now to get the velocity of the medium, we can take a partial derivative with respect to time. So we're not taking a derivative with respect to x. A derivative with respect to x would ask, how does one part of the medium compare with the displacement of another part of the medium, and another one, and another one? That's not what we're interested in. What we're interested in is calculating velocity. So we want to take a derivative only with respect to time, and that means we're going to be looking at one particular part of the medium at a time and measure how fast it's moving back and forth. So we get to take partial derivatives, and that means we can treat the x as being a constant. And that gives us a velocity formula of minus omega a cosine kx minus omega t. If we do one more derivative, I always feel like we got to do at least accelerations, right? Then we take another time derivative. That gives us minus omega squared a sine kx minus omega t. This all has to do with the motion of the medium. This is what an individual part of the medium is doing. And well, let's see what we've got in this question then. So here was a snapshot of the medium at some point, and then it's moving to the right, and so at a later time it's going to have shifted. Now individual pieces of the medium are oscillating back and forth at some given value of x. So their x value is not changing, their amplitude is, their d value is. Now at, so again, this is a t equals 0 and this is t at some later time. Here's the formula we're going to use. Now what we've had to do, and we did this back in chapter 14, what we had to do is we had to add in a phase angle. It sounds like in the problem that the function that we're going to represent the wave with, it's not going to be purely sine, and it's not going to be purely cosine. It's going to be some combination, or it's going to be a phase shifted value. So again, we did this back in the oscillations chapter, and we're doing it again here. So we're introducing the possibility of a phase angle. All right, now here's all the information given, and it gives a lot of information. The frequency is 250 hertz. Now frequencies in terms of cycles per second, in terms of hertz, that's not what we use in our formulas. Our formulas are going to be using omega. They're going to be using radians per second. And so that's what we've done first, or what I've done first here, is taken the omega and converted that into radians per second. So I'm going, okay, I've got that piece, because this is the formula representing the wave. So I've got that piece figured out. Now they flat out told us that the amplitude is 2.60 centimeters. So that's how far up and down, away from equilibrium, individual parts of the medium are moving. So I got the A figured out. So let's see, at what point have we figured out the whole function? I've got A, I've got omega. I still need the wave number, and I still need the phase angle. So let's see what else we've got here. It says that the tension is 140 newtons and the linear mass density 0.120 kilograms per meter. You know what I could use those for, right? So combining the tension and the linear mass density, square root here, the speed of the wave comes out to be 34.16 meters per second. So I've got a speed of the wave, and then remember that the wavelength, the frequency, and the speed of the wave are related by this relational formula, and I can use that to calculate a wavelength. The wavelength here, the distance from one crest to the next, is 0.1366 meters, and then finally, to get the wave number, 2 pi over the wavelength. That came, oh my gosh, that's radians per meter. I'm having a hard time with the radians units. That needs to get corrected too. So this is going to be radians per meter. This is in radians per second. K is radians per meter. It's a wave number. So that's 45.99 radians per meter. And then what we can do then is use, we've got K figured out, right? So omega we calculated, K we calculated, we're going to get the units corrected. This was given. The only piece left is that phase angle. And that phase angle, or phase constant, we can determine by looking at the initial conditions that they gave us. They told us that at t equals 0 and at the location x equals 0, that the initial displacement is 1.60 centimeters. Well, looking at this equation, if t is equal to 0 and x is equal to 0, then those terms go away, and the only thing left is a sine of the phase angle. So the phase angle can be calculated if we know the amplitude, which we do. So we can calculate the phase angle, and that's, let me skip a line here. So I'm taking this formula, bringing it down to here, and saying sine of phi is d 0, 0. That's t equals 0, x equals 0. So starting conditions for the displacement, 1.60. The amplitude is 2.6. And I can calculate the phase angle from that, 38.0 degrees. Now, it really should be in radians. And so I converted those degrees over into radians, 0.633 radians. So that's it. We got the whole formula figured out. But wait a minute. We know, again, from chapter 14, that this might not be entirely the only solution possible. There's going to be another sine solution where we take 180 degrees and subtract 38. There's a second solution out there. We don't know if this is the right one. So the other piece of information given to us was that the point we're looking for has a negative velocity. It said that that part of the medium is headed downwards back towards the equilibrium point. So I kind of scanned along here this wave pattern, and I said, where on the wave pattern would we be at a positive displacement but at a negative velocity? And I picked right there. See how that's positive displacement, 1.60 centimeters, but they told us that this part is falling back down towards the equilibrium position. And so I went with this point here. Now, the way we can check and see if we've got the right solution is to look at V 0, 0. So the V formula, which is not here, I got to go back to the page before. If we go back to this page, we can see here was the velocity formula. And notice that it's already got a minus sign here. Now, let's go forward then. So that says that at t equals 0, x equals 0, the velocity function will be negative omega a cosine of phi. That's going to be a negative value if we're using 38 degrees. So between 0 and 90 degrees, both the sine function and the cosine function will be positive. And so I think we've got the right solution this time. This 38 degrees, or more properly, 0.633 radians, that meets the requirements of 1.60 centimeters of displacement and moving in the negative direction. Okay, so questions on that? Again, stare at these formulas, go to a quiet place and think about them. We're going to move, well, I guess. Okay, last look. Yeah, we got to get that radians per second. That's radians per meter. Get that changed, or I'll get it changed. Let's see, let's look at a segment of a string under tension. Now I'm going to move pretty quickly through this. What they're showing is that if I have, here's a small part of a string, and there's a wave moving through this string right now, and so what's happening is that there's a tension throughout the length of the string, but notice the tension here is not exactly opposite the tension here because the directions are different. And so the net effect of a force here and a force here is to bring the string back towards equilibrium. And that's what they're trying to show here. Now, I always feel like these derivations are a little suspect. They always feel a little bit more like a plausibility argument rather than a really firm derivation. In any case, what this leads to is it leads to this. It leads to what we call the wave equation, and no, you don't have to derive this. So what it says is that the values, the functions of d, if I take two x derivatives, then that needs to equal 1 over v squared times the second partial derivative with respect to time. So these are what are called partial differential equations, and they're scattered throughout physics. We've seen a lot of differential equations, I think. In this case, they're partial derivatives on both sides. It's a one-dimensional equation. It's a linear second-order partial differential equation. And we're looking for a function of x and t. Now, we've already written this down. So we've already said, yeah, but this is the function we've been using. Let's check and see, is it going to be a solution to this differential equation that we've derived? Now, a couple things to keep in mind. The formulas that were, the equations, the wave equation, and the formulas we have here are idealized. They don't include any damping effects. So these formulas by themselves predict a wave that propagates forever without having the amplitude drop off. Or if they're spreading spherically, the drop off is exactly 1 over r squared. No thermal energy is generated along the way according to these formulas, and that's overly idealized. It's saying that the energy is conserved, mechanical energy is conserved within the motion of the medium. So the medium doesn't heat up as these waves pass through. So given those, given that limitation here, this is the formula we've been using. If we take a couple of partial derivatives with respect to time, the sign becomes a negative cosine and then a negative sign. Now, each time we're taking partial derivatives with respect to time, we need to bring out a factor of negative omega. So here I'm getting a negative omega, the sign turns into a cosine. Here I'm getting a second factor of negative omega, and the cosine is turning into a negative sign. So that's 1, 2, 3 negative signs. So I guess it stays negative. Now, partial derivatives with respect to x, there we would be bringing out factors of the wave number k. And so here is our wave number related to wavelength. And we bring out a factor of k. Starting from here, we bring out a factor of k, the sine becomes a cosine. We bring out a second factor of k, the cosine becomes negative sine. So in taking the two partial derivatives, we've got a negative sign on both of these. Two partial derivatives with respect to time gives us an omega squared. Two derivatives with respect to x gives us two factors of k, the wave number. So by the time we've taken two derivatives, what we've got is minus omega squared times the original function, and here we have minus k squared times the original function. Okay, so here's kind of a diagram of what's going on with the disturbance and the wave motion of the medium. So we can take those solutions that we've got. I'm going to plug those into the wave equation that was given. So it said take the second derivative with respect to x and take the second derivative with respect to y, to t, and then put a 1 over v squared here and see if it works. Now, what we've got to do then is go, well, what is v? V is the wave speed. So we really should have the wave speed written right here. So v is the wave speed, and that's going to be a wavelength over a period. Now the wavelength is 2 pi over the wave number, and the period is 2 pi over omega. So if I substitute those in, I can show that the wave speed is given by omega over k. So the radians frequency divided by the radians wave number gives us the wave speed. And that says that it's a match. The wave speed is given by omega squared over k squared. And when we plug these into the differential equation, the functional portions, the x and the t dependence, all cancels out. And what we're left with is v squared is equal to omega squared over k squared. And that is true. That's a true statement. That's how all of those values are related. So it worked. What we have really is a solution. So we really can use these sines and cosines as solutions for wave motion. Now, that's not the only solution possible, the sines and the cosines. What we can do is we can use what's called the principle of superposition. Let's say that we've got a material and we have a certain frequency that we're creating a disturbance. So there's a frequency at which a disturbance is being created, and it's creating this waveform within the material. Well, what if we add to that a different frequency? What if we have a disturbance that doesn't consist of just one frequency? What if it consists of many frequencies all happening at the same time? Now, you might think, well, don't things get really jumbled if we have a lot of different frequencies happening at the same time? But what we find is that we can take different amounts of different frequencies. In this case, they've taken 3 different solutions corresponding to 3 different omegas, and they've added them together to get a more complicated function. And this is referred to as superposition. So no, we're not limited to sines and cosines. So we can take any of these sines and cosines as a starting point. We can add them together. So we can add together these waves of different frequencies and different wavelengths. They're all traveling at the same speed, or at least we're going to assume that the speed of propagation through a medium is independent of the frequency. That's not necessarily the case either, but we're not going to unnecessarily complicate our lives right now with that. So I've got all of these profiles moving through. We can just add them all together. So it says I'm actually going to get a disturbance, a wave, with that funny looking profile traveling through. So down here it said that this is called Fourier's theorem, that you can take any number of sine and cosine functions, add them together, and that function will also be a solution. So once we've found the pattern of functions that are solutions to this, we can just add those together however we want. And that means we can create pretty much any shape we want. So we can start with any shaped function we want, and then we can make it time dependent so that it all moves together, that profile, either to the right or to the left. So that's easy enough to do mathematically. Now the complications here are, as this propagates, is there going to be damping taking place? Yeah, that's a possibility. We could, the amplitude could drop off simply because of damping effect. The material heats up a little bit. And then do all the frequencies, all the wavelengths of disturbances travel at the same speed? Maybe not. So we might actually have a separation of different frequencies with time. But for us, everything travels at that same speed, and we're not going to have any loss of into thermal energy. No thermal energy losses along the way. Now they've said that you can take any complex periodic wave, can be written as the sum of sines and cosines. Complex made me a little nervous because there's a mathematical definition. What they mean is complicated, I guess. Complex, that's a mathematical term for imaginary and real numbers, right? So I crossed that out. And it turns out they don't have to be periodic. If you take the right set of sines and cosine functions and add them together the right way, you can create a single pulse. So a single pulse can be frequency analyzed. A single pulse consists of a combination of different frequency solutions that look like this. So yeah, the pulse can have pretty much any profile that you might imagine. And again, if everything's propagating at the same speed, that profile will just be maintained. So it doesn't have to look like one pure sine or cosine. So here's an example. What they've done is they've taken the stuff from the previous page, the previous slide, and what they're saying is here is this much. They've got 1 meter. This should be D. They keep using Y. I should go back and change that to D everywhere because it's displacement. This is a meter. So this has an amplitude of a meter, and then they took this other frequency, and this has an amplitude of like 0.3 meters, and then they took another one at 0.2, and they added them all together, and look what it looks like. When you add those together at each location, you just add the sum of them. Oh, it's 1/3 and 1/5. I see. So, yeah, that's about it. So 1/5 would be 0.2. 1/3 would be 0.33, and what we've ended up with is something that's starting to look like what's called a square wave. Now, that might sound contradictory, but you know, anything that propagates is a wave, and so if it looks, you know, if it's a square pattern, that's fine. You could have a periodic square wave disturbance if it happens to be the combination of those particular frequencies. Okay, what else do we have to take a look at here? Here is reflection and transmission. So if I have, now this is back to being a single pulse. So I got a single pulse coming in, and this end of the medium is fixed. It's being held in place, it can't move. If that's the case, what we find is that we get a reflection, and the reflection reverses, it flips over. So if we have this end held in place, when it gets here, the force is acting on the wires, reset it so that it's traveling back in the other direction, but it's flipped over oppositely. Now, what happens if we leave this end loose? If we leave that end loose, we still get a reflection, but the reflection actually comes back in the same orientation. So that's kind of interesting. Whether the reflected will be inverted or whether it will just remain with a pulse in the same direction. So you can get these interesting kind of pulse effects with these waves too. Here's another effect we can take a look at. Let's say here is a lighter section, lower value of mu, and then there's a higher value of mu here. If you hit a boundary like this, you'll end up with a transmitted pulse and also a reflected pulse. You'll end up with both. And so at these boundaries, in terms of the medium properties, you can create these kind of effects. A useful concept for looking at propagations of waves, here we have a central source with everything kind of heading out in a spherical pattern. And so we're thinking of these as individual rays showing what direction the waves are traveling in. And what we can do is we can identify a location where everything is at the same phase. So everywhere along here is referred to as a wave front. Let's say that this is air, and we've got a speaker, and there's sound being generated. And so here is some sound being generated from a speaker right here. What happens then is, if we have something that rises and falls, then maybe this is a crest. Everywhere along here is a crest, so that would be a compression within the air. So here is a region where the air is compressed, and then here is another region where the air is compressed, and here is another region where the air is compressed. Now that would say that there is one wavelength between those wave fronts that we're talking about. And it also says that the region halfway between would be a region of rarefaction, a region where the air molecules are a little bit spread out. A rarefaction gets generated in that region. Now this would be for something spreading out away from a central source. This is more like our beam effect. So once you get far enough away from a source, the direction of travel of the disturbance, the wavefronts tend to become almost planar. So here we're thinking of them as being spherical shells, and here they're planes. So once you get far enough away, you can treat these as being planar. I think we got everything said there. So again, I'm probably going to be using this idea of wave fronts. So wave fronts are really handy vocabulary to talk about, you know, where are all of the crests located. Now here's a reflection. Let's say that we have, again, it could be sound. So here is a disturbance, maybe it's sound passing through air. It hits a surface, and then it reflects back. Now what direction will it reflect in? And what they're showing is there's a series of wave fronts. So here are all the wave fronts coming in here. And each time a wave front hits at that surface, so here's a wave front coming in, we're going to see the wave front reflect back away from that surface. But when we look at the interference effects between the different points where it's hitting, it turns out that the reflected path of the wave is at the same angle as the incident path of the wave. Now we've drawn a normal here. The angles are being measured relative to a normal that has been drawn along that surface. So again, angle of reflected sound, angle of incident sound on a planar surface here. Those angles are going to match. Here's another interesting effect with interference. Let's say that we've got a cable set up, some amount of tension. We set a pulse going in this direction. We have another pulse in this direction. They're headed oppositely. What happens when the two pulses cross? Well, superposition tells us that at the location where these cross, they will tend to cancel each other out. Now, that says that if this pulse has exactly the same profile as this one, but they're just traveling in opposite directions, there's going to be a moment in time when the two pulses are gone. But it also predicts that the pulses will pass through each other, and that at a later time we'll see the two pulses emerge from that straight line, from that cable. How is that possible? And what we have to remember here is, even though the displacements have gone to zero right here, the velocities have not. The medium velocities. So here, what we had was individual pieces of the medium are moving back and forth as this wave goes by. And it says that hidden inside here, there are parts of the medium that are still in motion. So there's a part of medium here that's moving in this direction, and there are parts of the medium here moving up. And given a little more time, the wave reemerges and heads off in this direction, and the other wave reemerges and heads off in the other direction. So the medium is still moving, even if at that instant, the string, the cable, is just looks like it's flatlined. Now, what would happen if we had two pulses that pass each other? Well, the pulses just add together. So we're going to get a pulse with twice the amplitude at a particular instant. So as these two waves come together, those two pulses, we're going to see a larger wave develop in the middle, and this is kind of a peak of that, where we've got twice the amplitude, and then they'll separate as they pass through each other. So interesting effects, huh? And here, again, this goes under the category of interference. If I have two waves coming from, say, different locations, entering kind of the same region, if they show up in phase with each other, meaning that the crests match, the upper crests match and the lower crests match, then those two effects will just be added together. Whereas if they're out of phase with each other, this is like noise canceling equipment. So if there's a lot of noise around, you can buy earphones that will sample that sound and rapidly create a sound that's exactly out of phase, and the idea is you don't want to hear any of it. You don't want to hear any of that noise. Okay, and then in this one, it's somewhere in between. So it's not completely the first one was completely in phase, Next one was completely out of phase, as well as having amplitudes that would that match, so to get perfect cancellation. And here it's something in between. So again, this is superposition, leads to interference effects. All right, let's take a look at what are called standing waves. Now, up until now, we've mostly been looking at what we call traveling waves. And so traveling waves, the profiles move from one location to the next. Now, with standing waves, what you can imagine is taking a string, creating some kind of a disturbance, and I'm holding onto the string here. The string is fixed on this other side. That's referred to as a node. And so as I vibrate the string back and forth, what's happening is it looks a lot like a wave, but it's not going left or right, or at least it doesn't seem to be. So we've set the string into motion, and then we're just creating another node. Now, you can also set this up in a manner where you create a node in the middle. And you can create any number of these nodes. Now, the place where the string is not moving is referred to as a node. The place where we're getting the largest amplitudes are referred to as antinodes. I think that's brilliant that they came up with the word antinode. So what's going on here? What is going on with these standing waves? Okay, so here is some kind of a string. It's got a length to it. We're going to lift this up and let go. These are the different wave patterns that will persist. So what happens with a disturbance like this is it's going to propagate. So I create a disturbance somewhere along the middle of the string, maybe this is a little off to the side. And what happens is, initially at least, we've created a single pulse which consists of a wide range of frequencies, but very rapidly all of those are damped out. All of the frequencies are damped out and eliminated, except for those particular wave patterns that fit the boundaries. So in math, these are referred to as boundary conditions, and it says we need a function that maintains zero displacement at this end and zero displacement here. And it does turn out that, again, these turn out to be sine or cosine functions. So harmonic functions turn out to be the solutions, but now that we have the boundary conditions in place, there is what we call discrete solutions. This wavelength will work. This shortened wavelength will work. This is half the wavelength that this is, but something intermediate won't. There's no way I can get something with a value of wavelength between harmonic 1 and harmonic 2. Something intermediate won't fit the boundary conditions. It won't match up with the nodes. And so standing waves are going to take place here. In this example, when we have nodes fixed at both ends, then we're going to get a series of possible solutions, a series of what we call discrete solutions rather than a continuous set of frequencies. We'll only have certain frequencies that can be generated. Now, this is referred to as the first harmonic, the second harmonic, the third harmonic. This is also referred to as the fundamental. This is referred to as the first overtone and the second overtone. I'm going to probably stick with harmonics, label them that way, so I can label them as 1, 2, 3, 4, 5, etc., kind of on. And you can kind of see the pattern of what this looks like. Now, what's remarkable here is we've got these intermediate nodes, but there's nothing holding that in place necessarily. The reason those intermediate nodes work is because the tension in the string around that point at all times is equal and opposite. And so that is never lifted away from that equilibrium position. Now you would say, well, how do we create these? And again, depending on how we set up that initial disturbance, we're going to get some amount of all the different harmonics. So if it's a guitar string, for example, depending on where you pluck the string, where you set it where you create the disturbance, you're going to end up with possibly some combination of these different harmonics all happening at the same time. All right, now they've written down some formulas here. Let's take a look and see. First of all, how do the wavelengths compare? So in this one, the wavelength, that's not a full wavelength. A full wavelength would be going all the way over and then curving and coming all the way back. These three lines that they've drawn, those are timelines. They're showing what happens over time. So we start here, and then we go back to equilibrium, but then we overshoot. And then we go back to equilibrium, and everybody moves in the same direction together. In the second harmonic, this part, the left side, is displaced here, while the right side is displaced here. And then vice versa. So what happens is, we've got oscillations where the two sides are on going in different directions at all times. Here with the third harmonic, the one in the middle is going down while the two on the side are going up. Then when these come down, this one's coming up. And you can kind of, extend that, extrapolate that into what all the harmonics look like. So the wavelength here would need to be 2 full lengths L. And that's what they've got is lambda 1 is equal to 2 times L. Now here, wavelength on harmonic 2, that's like taking the 2L and dividing it into, here it's like taking the 2L and dividing by 3. So the general formula that we get, and try this out, the general formula we get for the wavelengths is like 2L over n, where n is an integer value. And that comes from the fact that the string is fixed at both ends. So those are the only wavelengths that are possible. Now what does that say about frequencies? Well, that says then that the frequencies should be given by v over lambda n. So there's going to be a different frequency for each one of the wavelengths. So depending on what the wave speed is, we can determine what that frequency is. Now, the wave speed for this string is going to depend on the tension, and it's going to depend on the linear mass density, those, the things that we've already been looking at. So, and again, this is going to depend on integer values. So the nth harmonic is going to have a frequency that's n times the first harmonic, or the fundamental. So we get a pattern of frequencies for a string attached. So think in terms of musical instruments here. Why do musical instruments have the sounds, or string instruments have the sounds that they do? And, a string instrument, again, is going to consist of some number of harmonics where the harmonics have a pattern. If this is 100 hertz, this is 200, this is 300, the next would be 400. The series of frequencies are multiples of the fundamental frequency. So if you're familiar with tuning instruments, if this is a string that's been tuned to A at 110 hertz, then this would be at 220 hertz, which would be another A. This would be at 330, 440, etc. All right, so those are the formulas. Here is now an example. It's a piano string. It's a meter, 1.10 meters long, and it has a mass of only 9 grams. how much tension should we place the string in order to have a frequency of 131? All right, so here is the piano string. Piano string's right here. It's the first harmonic that we're looking at, so if they don't say anything else, they're assuming that first harmonic. So I'm just going to jump right in and say here is the first harmonic. The string has a length of 1.10 meters. The mass is only 9 grams. We want to create a frequency of oscillation of 131 hertz because, hey, it's a piano string and we want it to have a certain pitch. And the pitch depends on frequency. Now we're going to be using the first harmonic. That means that the wavelength then, 2L over N, the wavelength here is 2.20. Now the wave speed can be determined by taking frequency times wavelength. So it says, look, for this piano string in the first harmonic, the wavelength is 2.2 meters. And if we want a frequency of 131 hertz, then we need to tighten the string until there is a wave velocity of 288 meters per second. So we've been able to calculate what the wave speed for the string would be. The wave speed, we said, is related to the tension and the linear mass density. So let's solve this for tension. T then we can calculate as mu times v wave squared. We got the wave speed. What we have to do now is get that linear mass density. And that's going to come from taking the m and dividing through by the L. And that gives 0.00818 kilograms per meter. Plugging that in, we end up with a tension of 680 newtons. So I don't think this is the way the piano tuner comes and tunes your piano. I don't think they measure the tension to get a certain, I think they listen to the pitch. But anyway, this is the tension that we're calculating you would need for this particular string. Now moving on to part B, it now asks about the first 4 harmonics and says, look, if the first harmonic is 131 hertz, what will the pitches, what will the frequencies be for the other harmonics 2, 3, and 4? And there's more harmonics than those. Now, this is just kind of a review. We learned how to calculate the wavelengths. So the wavelengths are definitely different, and they're all related by that formula. We also learned about the formula relating frequencies and wavelengths and wave speeds. And then we also have the formula telling us what is it that actually determines the wave speed, and that's the tension and the mass. So putting all that together, here is our frequency formula, and it says the frequency of the nth harmonic is n times 1 over 2L times t over mu to the 1/2. Now, so how do we get a string to produce a certain frequency? Well, first of all, when you build the instrument, maybe it's a piano, maybe it's a guitar, maybe it's a violin, we have to think in terms of the length. What length of string is going to be free to move back and forth? That's L. And then we can decide how heavy the string should be. And if you've noticed on a guitar, for example, the strings that are going to hit the higher pitches, the higher frequencies, have lower values of linear density. They are thinner strings. The thicker strings are producing the lower pitches, and the thinner strings are producing the higher ones. And then finally you can tune the thing. So you can tune the guitar, the piano, or whatever, and adjust tension. Now that was just all kind of a review. What we want to take from this is what the first harmonic formula looks like, and to get the rest, we just multiply by n. So we talked about that on the previous slide. So since they've already given us the first harmonic, I can just multiply that by 2 to get the second harmonic frequency, multiply it by 3, multiply it by 4. I can multiply it by those integer values to get the other frequencies. Okay, so here's another example here. it says that we have two waves traveling in opposite direction. Now, they haven't shown this. I feel like they haven't shown this very, very well. Let me jump ahead here. So what they're talking about in this problem is we've got a string, maybe, and we're going to send two disturbances in opposite directions. We looked at something similar to this. What we should be able to do is determine what, adding those two disturbances together, what will that create? So what I'm going to do is I'm going to start with wave number 1 and say that its displacement as a function of position, as a function of time, is written as amplitude sine kx minus omega t. That's moving to the right. d2, the function d2, is going to describe the motion of the medium of this wave going to the left. So to do that, I just changed it to a plus sign. Now, a couple things you'll notice about these waves. They're not completely random. They both have the same amplitude. They both have the same wave number, which means they both have the same wavelength. They both have the same frequency, which means that they both have the same period of oscillation for each part of the medium. So in many ways they match, except they're going in opposite directions. So what would happen if we created a superposition of two traveling waves? These are traveling waves, and what we're going to find is that's a standing wave. So standing waves, mathematically, are actually a superposition of two traveling waves with the same amplitude, the same frequencies, the same wave number, but traveling in opposite directions. So yes, the standing waves are going to be solutions to the wave equation that we saw earlier. Now, if they're standing waves, what determines their velocity? And it's the velocity of the two waves that combine to create the two traveling waves that combine to create the standing wave. So it always seems a little funny at first when you go, wait a minute, standing waves, why do the standing waves have a wave velocity? It's because the standing waves, mathematically, are two traveling waves headed in opposite directions with the same amplitude, same wave number, same radiance frequency. Now, in the back of the book, or you can go online, there is this nice trig identity that allows us to add two sine functions together. Now, they don't have to be sines, they could be cosines, or they could have phase angles, but we kind of kept this as simple as possible to see what happens. So if I take sine of theta 1 plus sine of theta 2, my trig identity says that's 2 times the sine of theta 1 plus theta 2 over 2 times cosine of theta 1 minus theta 2 over 2. Now, you may remember this from your trig. This is one of the, I'm going to say this is one of the more useful trig identities. For many students, trigonometry was so traumatic that you've blocked it from your memory. You can't remember any of these, but they're in the back of the book, especially the ones that are relevant for physics. And so this is one of those that's really handy to show that two traveling waves can be combined. Now, if I take that and apply it to these two functions, the sine 1 plus the sine 2, theta 1 is going to be this argument, and theta 2 is all of this. So theta 1 plus theta 2, if I add these two together, I get 2 kx's. The omega t's cancel out. And so what I'm left with is the sine, and that's divided by 2, the sine of kx. Now, similarly, if I take the difference of these two arguments, the kx's cancel, but the omega t's add together. Now, you may worry that is this theta 1 minus theta 2, or is it theta 2 minus theta 1? And it doesn't matter because it's a cosine, and cosines are even functions. So we can drop the minus sign. We'll divide by 2. What happens when we add two traveling waves, mathematically, is we get a function, d1 of x and t and d1 of x and t, that is 2a times the sine of kx times the cosine of omega t. what does that function look like? And what has happened now is it's no longer traveling. What's happened is we've taken the spatial component, or the spatial factor, and isolated that from the time factor. The traveling waves depended on kx minus omega t. This one doesn't. So what that means is that, let's think of this first. So what I've got is I've got a wave pattern, a sine function, that's in some region of space, but it's not moving. It's not going left, it's not going right. Instead, it's being multiplied by a time factor where every part of this function, the spatial portion, moves together. So now when we talk about synchronization, it's everybody's on board kind of together. So when we look, at least at the first harmonic, it's very clearly that way. So the first harmonic, all parts of this oscillate together. Now, in the second harmonic, and the third and the fourth, there are these intermittent, these intermediate nodes. And so, but still, everything is reaching maximum amplitude at the same time, possibly in opposite directions. So that's just kind of interesting, I think, that the superposition occurs so cleanly. And so in this particular example then, what we've done first of all is shown mathematically how this happens. You can also do this with diagrams showing the superposition. And then taking this function, they told us this was, the amplitude is 20 centimeters, k is 2 radians per meter, the wavelength is 3.14 meters. I'm just trying to get that list of everything we've talked about. And I think that's important. Go through, kind of do that comprehensive, very thorough list of what are all the properties of this standing wave that we've come up with. Here is its wave number, its wavelength, its frequency. Oh, that was given. Okay, I got to go back, and one more item we got to talk about here. Okay, so what textbooks like to do is they give you these functions. You know, this is the amplitude. So I'm just going to write that down as big A. What's in front of the x is the wave number. That's the wave number k. And then in front of the t is omega. That's the radiance frequency. And so that's what I've done. I've read those numbers off. I have, in my opinion, I have returned the function back to the form we should be writing it in terms of, with symbols instead of these numbers. And then off to the side, you can write down what the numbers are. This is 20 centimeters, this wave number is 2 radians per meter, and omega is 4 radians per second. So that's the function that they wanted us to derive. And then they asked this. They said, let's pick a certain location and ask, what's the maximum amplitude here? Now, the maximum amplitude overall, is going to come from adding these two together. There are going to be places along the standing wave where the 20 centimeters and the 20 centimeters, that's a lot of amplitude, they just add together. Yeah, 20 centimeters is like this, so it's not a guitar string that vibrates back and forth 20 centimeters. Anyway, those are just going to add together. If we look at a particular location along there, and they are looking at the value of 0.45, we plug it in. So I take the 0.45, plug it in for x, plug in the k value. Now it wants to know what's the largest displacement. To get that, I set the cosine equal to 1. So the cosine was set equal to 1. It says at this particular location, when I take the sine of kx, 2 radians times 0.45 meters, I'm getting 0.783 for that. So this part of the string only vibrates to a maximum of 31 centimeters. Okay. Yeah, so it's like 40 centimeters in both directions. So if the equilibrium is here, it goes 40 centimeters this way, and it goes 40 centimeters here. that's a lot of amplitude that they have in that example. Okay, so superposition is going to be super important, right? So make sure that you're looking. I think there's a couple of homework problems on superposition. Definitely take a look at those problems. Now, we had talked about wave fronts before. So let's say that we have a disturbance with a set of wave fronts. These are the crests, and there's a wavelength here between them. What if they hit a boundary between two different materials, and what's going to happen is the wave speed's going to change. You know, the wave speed in one material with some density and some elastic properties will not be the same in some other material. So it could either speed up or slow down. What that leads to is actually a redirection of the wavefronts. So this thing that they call a ray, that's just orienting us as to what direction the energy is being carried by the wave. Now there's a formula here, and we'll derive this in a second, but what we find is that the ratio of the sines of angle 2 and angle 1, okay, so I guess the 1 here means this is theta 1, it does, and then the 2 here means that this is theta 2, but they wrote them as incident and refracted. This effect is called refraction. So you can have these disturbances that hit a boundary with different materials, and it redirects it. And so here's kind of a derivation of what's going on. So here is this wavefront. Now I can think of that as a series of arrows, of red arrows. The direction of velocity of the wave is going like this. And what's happening then is that when it hits the boundary, it slows down. Now, why does it bend? And kind of jumping between these last two slides here. So here's two possible paths that the disturbance is traveling. This part of the wavefront reaches the other material first and slows down. So they've told us that it's going slower, or that's what the picture is telling us. So it's going slower here, while this part of the wavefront continues to go fast, and then at some later time hits the boundary. So what we want to match up is how far did this path travel during time t versus how far does this one travel during time t. And what that will tell us is how the wave direction will be redirected. So I have to tip my two paths, I have to tip my wavefronts so that the wavefront coming away matches up with this triangle right here, and the wavefronts coming in match up with this right triangle. They're both right triangles coming in. Now, these two triangles share a hypotenuse. Hypotenuse is the same, but the distance traveled here, L1, is equal to V1 times t, the higher speed, times t, whereas this length is shorter because V2 is less. So if I go into a material, if the disturbance propagates into a material where it's traveling more slowly, it will redirect itself so that the angle is closer to the normal than it was when it was going faster. Faster speeds, farther from the normal, slower speeds, closer to the normal. The angles decrease. Now, sine 1 from this diagram is L1 divided by, now they're calling this distance A, the hypotenuse of the two right triangles. So that's L1 over A, and L1 is the same thing as V1t over A, sine theta 2. So theta 2 is here. Now that's L2 over A, which is V2 times t over A. So if I take the ratio, if I take sine 1 and divide by sine 2, the t's cancel out because it was the same time interval that we're talking about here. And the a's cancel out, and we're left with V1 over V2. Okay, so let's try this. Here is another earthquake problem. No, it's not the San Jose quakes, but it's an earthquake problem nonetheless. Let's see. It's going to speed up. So here is an earthquake, a disturbance from an earthquake, passing from one type of rock into another where it speeds up. What angle will it come out at? So here's that formula we just derived. Now they told us it's actually going to speed up. So that means that the angle here is well, the angle here is 30 degrees. And then when we speed up, we'll go to a larger angle. So this will refract into a larger angle. And so I can put the numbers in, sine theta 2 over theta 1. Sine theta 1 is V2 over V1, which is 8 over 6.5. That worked out to be 1.23. And then theta 1 is given. So you just go in and solve for theta 2. And theta 2 works out to be 38 degrees. So it came in angled at 38 degrees relative to the normal. And the normal is defining the boundary. So there's a surface between these two, different rock materials, different densities, different elastic properties. And that normal is the reference we use to measure the incident and refracted angles. So it goes from 30 degrees to 38. Now there's other type of wave interference effects going on. Here, what is this created in? Is this, it's not water, is it? Maybe it is water. So here is, it better be a mechanical something. So here is some kind of wave set up in a medium, and you can see that there's a shadow region behind it, and this is referred to as diffraction. So when we look at wave patterns, see how we have these nice straight wave fronts, and then there's an obstacle, and the waves have interference effects that take place around those obstacles. So here's another example of this. Here's some blades of grass where the waves just kind of go right through. The obstacle is much smaller than the wavelength. Wavelengths are from one wavefront to the next. But then we get to a bigger stick, and you start to see this diffraction effect more pronounced. And then they're showing as the short wavelengths come in, you see the diffraction effect more prominently. But when you have wavelengths that are similar in size to the obstacle, the diffraction effect isn't as pronounced. So, all right, and that takes us through chapter 15. Okay, so if there's any questions, stop by office hours, let me know. I'm hoping to see a number of you, maybe all of you, during office hours. Bring your questions, we'll get those looked at.